Hi everyone, my name is Amit Gross and today we're going to talk about what is the expected cost to create a machine learning model. So an overall machine learning solution usually comprises of these major factors. The first factor is the cost of storing the data. It depends on the amount of data that you need to store and the type of the data that you need to store. So obviously text data storing costs less money than storing image data, which costs less money than storing video data. It also depends on the resolution that you need to save your data in order to do a proper training. So if you can save your data in a lower resolution, you'll be able to cost a lot of money during this storage phase. At the same time, if you can run your model not every hour or every day, but once a week or once a couple of days, you might be able to store your data in a cold storage and not a hot storage. And usually the compromise will be about the speed of accessing the data. The next major phase is a research phase, and usually this is the longer phase from all the other phases. And researching usually requires some interactive accessing to the data. Usually researchers, data scientists, analysts do this with a notebook kind of development using their IDE or some remote IDE. So if you'll use a remote IDE or remote notebook, usually you'll need to preserve some remote notebook instances in the cloud. All the cloud providers today has it, but they all have it, but it costs money. So in the research phase, if your researchers will be able to shut down those machines while they're not developing, it will cost you less money, obviously, because those machines will not be alive and you will not pay for them. In this phase, if your researchers will be able to work offline, meaning locally on the data on their local computer, on their local notebook instance or the local IDE, obviously it will cost much less data because this is their home computer. In order to do this, they will do some kind of heavy lifting on the data in a cluster on the cloud. But once they have a result or a normalized data, they can download it into their own computer and try some various algorithm locally. This usually saves a lot of money during the research phase, and it's really recommended. However, you need to do it carefully in terms of security. So this is the research phase cost. It also really depends on the ease of accessing to the data. So if your data is not normalized or filtered or accessible to your researchers, then they have to make some ETLs in order to move the data from one storage to another storage and do some manipulation on the data, some filtering on the data, normalization on the data. Usually those ETLs or crawlers cost money. And they usually, if you use some cloud-based solutions, they will cost the cost will comprise on the amount of time that you run these processes. The productization phase cost, this is also a major event, which usually comprises of training the model, running on some cluster. We will talk about it in the next slide, and serving the model in real time. This also really depends on the solution that you will be making during the research. The fourth major phase is the validation phase, when you need to check if your model actually works as expected in a real-time environment, in a production environment. And usually it will require some reports That really depends on your reporting system, if it costs money or this is some kind of tool that you've developed in-house, in order for the researchers to test and validate and monitor what happens uh, with the model and the results. And there are also solutions when you have to test various models in order to see which one brings you the best solution, the best result, which requires also a machine or mechanism for an A/B testing. The last major phase, obviously, this is the maintenance cost. As in any engineering solution, this maintenance cost depends on the customers, the amount of customers. You might need to extend the machines that's serving those customers, or you need some more data in the training as your customers base is larger. So the machine learning model depends on the needed solution. Most of the solutions in the market today use some batch learning, offline learning, and a real-time inference. This batch learning requires you usually to hold a cluster in the cloud. This cluster comprises of some kind of an Hadoop system with many computers, and it really depends on the amount of data that you need to run your training on. So usually in any cluster, you have some master node, core nodes, and task nodes. And the cost of preserving the cluster, it really depends on the type of the machines. We'll talk about it in the next slides. And of course, in the how you can generate some cost saving in this cluster in terms of how much time you need to run this solution. And the real-time inference is the serving layer that is usually connected to your product, to your engineering components. And this more depends on the amount of customers that you need to serve. So as I mentioned, most of the machine learning solutions are offline solution with a real-time inference. In some cases, you need some online machine learning. Online machine learning is, let's take, for example, a stock exchange, when there is a time series of data and you need to generate some predictions in real time. And usually in order to generate this kind of solution, you need some windowing mechanism in the cloud in order to get the data and store it to some amount of historical data and then run your learning on it. Usually these solutions are more complex solution. You might need to use some incremental learning in order to avoid the catastrophic forgetting, meaning that your model will not take into account some historical data because it will look only on a specific amount of time in a window frame. So usually you'll need some incremental learning approach that your model will evolve and the historical model will preserve the results for you somewhere, and then you can just take the results and adding the data, the newer data together. So as I mentioned, these are more complex solutions which require more real-time resources, usually more memory, and memory is one of the most expensive components that you can put in your production system. So the offline learning, the batch processing, as we mentioned, it needs a cloud-based cluster to process the data. This cloud-based cluster, as I mentioned in the previous slide, requires some master node. This master node need to run always and cannot be shut down. because in an Hadoop system, in a distributed system, once you shut down your master node, all the all the memory of where the data is located in the cluster is lost, and your cluster is useless. So in most cloud providers, you have many types of instances that you can preserve. There is a long time preserving instance, usually for 1 year or many years. This will usually cost less than an on-demand hardware that you need. An on-demand hardware is usually the most expensive. So note that if you'll need this cluster for a long term, you might want the master node to be some kind of a long-term instance that you can reserve instead of an on-demand hardware. Then you'll need a core nodes or task nodes, which will usually process the data. They will run your filtering, normalization of the data, and even the modeling of your machine learning model. And I really recommend you to use some spot instances in your cloud provider. Those spot instances are instances that your cloud provider usually have some available hardware that is available for instant use, and usually it costs 80% less than an on-demand instance. So how to build your cluster is really important in terms of the amount of machine, the type of machine, and the type of instance that you can preserve and to lower your cost. At the same time, note that you might need some development cluster, and it really depends on how you would like to work. Usually I work on the production cluster during the research as well, in order to save money. The type of machine is really important. So if you need to manipulate and work on images data or video data, then you might need some GPU-based machines. Those are more expensive machines, usually 4 times more expensive than a CPU-based machines. If you work on images and video, you might need more machines like this, but you might be able to reduce the amount of machines, because every GPU-based machine is really strong. So you might need less than if you would work on a CPU-based machine. So if you need a model with deep learning and you need some TensorFlow or Keras that is working on some kind of MXNet or TensorFlow neural network, then those GPU machines are must. But again, you might need less machines. So it really depends on the architecture that you're building. Training the data. So training the data really depends on the solution that you're trying to build. So whether this is an online training or an offline training, this is really important. You might need some memory, high memory. So if your architecture is a neural network, you need some higher memory-based machines. Memory usage is really more expensive. So try to save on memory during your training. You might not need all this kind of memory if you're not building some incremental learning solution, or if you're not building a very complex memory-based architecture of a neural network. So always try to convert the memory problem into storage problem. It will save you a lot of money. And if you are doing an offline training, this is usually the recommended uh, way to work in order to save money. So as I mentioned, it really depends also on the architecture that you're building. Saving intermediate and final results also cost money. So uh, keep in mind that you don't need to save too many result sets or data frames during the training. As you'll save less data, it will cost less. These are usually not so dramatical during the training because most of the money will go for the cluster and processing the data and the machines in your cluster and to storing the data. So productization phase, the serving of the model productization, it means that in real time, you need to combine the serving layer. Once your model is ready after the training, then you'll need to serve it into some product or the solution that is working with it in real time. And, and usually there are many types of how you can serve your data. It can be some Lambda architecture, some serverless architecture that start a server and then serving the customer once he requests the solution and then shutting it down. Usually these are the kind of serving layers that you'll need because it will not run always. It will have some starting time and it depends on the solution that you have. Today you have other solution like endpoint serving layers. You can find it in Amazon SageMaker or in Microsoft HD Insights or other solutions. Note that these solutions, usually when you define them, you need to carefully check the amount of instances that are default. Usually it will not be one instance, so make sure that you have the amount of instances that you need. I recommend starting with one and then testing the results and the real-time latency of the solution, and then upgrading it as you need. And so check the default when you're building those kind of solutions. And usually those endpoint cost a lot more money, as you can see in the graph above me right here. So it will cost more money than just a trivial serverless solution. So make sure that the machine that you run your endpoint, the default machine, is not a super strong machine because you might not need it in real time. It really depends on the concurrency requests that you have in real time and the amount of real-time data normalization that you need to do in real time. So if you need to take a video, for example, and then to manipulate it before running the model, you might need some uh, stronger hardware in your real-time inference. And this might requires some more heavy lifting real-time processing, might even be a GPU-based machine. And note that caching is also a good practice in real time because you might need to preserve the responses that coming from your model and to take them into account in your next inference, in your next prediction. So note that caching is really expensive because this is a memory-based solution. If you can avoid it, it will be great. But usually this is a good practice if you need some consistency in your results because machine learning comprises of statistics. So it's not deterministic. Your prediction might not be deterministic, and you might need to watch your historical responses in order to generate some good result serving. So as a thumb rule, the batch processing, the training, usually cost 90% of the overall solution, meaning from of the serving solution. This is not the case for online learning, but as I mentioned before, most of the 90% cases in machine learning are offline learning. Um, so note that in these cases, um, you might be able to cost to reduce the amount of cost and try to see how you can save on the training phase rather on the real-time inference phase. And as we mentioned before, note the memory extensive machines or the memory data, memory-based data that you're preserving during the training or the serving. This usually more expensive. In depends on the maturity of your solution. You might need some more components like model versioning if you need more models, and if this is a cloud-based solution, then it costs money. Usually, it's a good practice to combine all those um, components like a model versioning or model monitoring solution and just put it on your master node in the cluster. This is the best practice because your master node, as we mentioned before, it will be an always running hardware. So as the more component that you put on this hardware will cost you money in terms of not generating specific instances for every component. So last, try to reduce the training cost. One of the best things that you can do in order to reduce your training cost dramatically, as we mentioned, the spot instances, but also shutting down your cluster. So if your training does not require to run every few hours or once a day, even if it's once a day, then during the day when it's not running, you'll be able to shut it down. So usually a good practice will be to do some job that will start your cluster. It can be a notebook instance cluster, or it can be in Amazon, this is an EMR cluster, or Microsoft cluster, or cloud computing, Google. So all those clusters cost a lot of money when they're working because they have nodes that are constantly running. That's the master node and one of the core nodes, and they usually expand and reduce. And this is the configuration when you build this cluster. So make sure that you might not need some auto scale for this cluster, because otherwise your cloud provider controls the amount of machines that you have, and it's not you that you're controlling the amount of machines. And do some in your configuration of the cluster, try to determine the max amount of instances that you will need. Try to do some calculation on the amount of data and the historical data that your model needs to run on. It might not need to run on all the historical data, but only on the last month of the data, on the last 3 months of the data. So once you can define this maximum amount of instances, it will reduce the cost. And once you can start the cluster, do the training job, and then stop the cluster, it will save you a huge amount of money. The last quote is negotiate with your cloud provider. Once your training of your model is completed, then you can negotiate with your cloud provider because you know the amount of servers that you need. You might be able to just test in many cloud providers how much money you pay for the same cluster running on multiple providers, just for testing and just to have a negotiate point with your cloud providers. Usually you, once you negotiate with your cloud provider and you have a big solution, from my experience, you'll be able to save about 30% of the cost. So this is very dramatic. Thank you.